So when people find out that I'm a programmer, one of the first questions they ask me is, or the first things they tell me is like, oh, you must be really good at math. The show of hands here, who's heard this before when people find out you're a programmer? Yeah, we got a lot of hands. How many of you would consider yourselves actually good at math? Okay, a few hands, not quite as many. So my name is Joël, and I am not good at math. In fact, as a Rails developer, I mostly just use basic arithmetic, the kind of stuff you can do on your fingers, the kind of things that just about everybody else uses in their jobs as well. But recently, I was having a conversation with someone about what is the most useful CS class for the working Rails developer. Because there's a lot of theory, there's a lot of interesting things, but what's actually useful for us writing Rails? And let me tell you up front, it is not data structures and algorithms. I know, right? Dropping the hot opinions early in the morning. So I thought a while, and eventually I settled on discrete math. And this surprised me, and it surprised people I was talking to. But it turns out that this is actually a skill that I use on a daily basis. So what is discrete math? Discrete math is a bit of a grab bag, and it has little bits from a variety of mathematical disciplines. So we've got some propositional logic, some Boolean algebra, some graph theory, some set theory, some combinatorics, some probability, some predicate logic, and a few other fields as well. Now today, we're not going to dig into the theory of all of these fields. Instead, we're going to look at a series of practical problems and what are some ways that discrete math informs our solutions to these. Our first one is unnecessary conditionals. Now, conditional code and if-else expressions are a core part of programming Ruby. They're one of the first things that you learn. And when I was a brand new developer, I wrote a lot of code that looked like this. So this is some permissions code. Yeah, you all see it, right? So we're saying if admin, return true, otherwise return false. And this is perfectly serviceable code, but the conditional is entirely unnecessary because it could be simplified down to this, just calling the admin Boolean method here. So a lesson that we can learn from Boolean algebra that is relevant here is to concentrate on operators. Boolean algebra is a field of math that deals with Boolean values, true and false, and operations that can happen on them. Now that's pretty basic. These are things that we learn in probably intro to programming, but there's an entire field of math built on just those simple elements. So some common Boolean operators and operations we might want to do. First is just identity, returning the value itself. And that's what I had accidentally implemented in that conditional you saw. Secondly, we might want to do negation. In Ruby, we do this with the exclamation mark operator. And then there are a couple ways that we might want to combine two Boolean values. We can combine two values with an and, or we can combine them with an or. So we already saw earlier that sometimes we only want to use the admin value directly. So this is doing identity. But here's another example of something that we might have a conditional that's unnecessary. And I've written plenty of these. So here we're saying if admin return false, else return true. Very similar to the first one, except the two branches are flipped. And this is really just re-implementing the not operator. We're doing negation here. Let's look at something a little bit fancier. So at first glance, you might look at this code and say, that's not a conditional. But see at the end of the first line, we've got that trailing unless. And that true on the second line, that's an implicit else. So we've got some conditional code happening here. And this is actually equivalent to Boolean OR. Honestly, in my opinion, this reads a little bit better as a Boolean expression. To say who can edit an admin post? Well, you can edit it if you're an owner or if you are an admin. And now I don't need to parse a complex conditional expression in my head. So the first lesson that we get from discrete math and from Boolean algebra in particular is lean into operators. If you're doing a Boolean expression, don't try to re-implement everything with if, but use the tools that come with the language. Okay, so you've written some code, you've made it better on your own, but what about other people's code? What if we're doing a code review and that weird conditional we saw earlier is written by a colleague? And we're looking at this and we're trying to understand what happens, and we're feeling a little bit, huh? What exactly is going on here? Well, the field of propositional logic gives us a really helpful tool that we can use in this situation. It's called a truth table. I love these. So the way they work is that there are two values that influence the result, whether someone is an owner or whether someone is an admin. We're going to put those in two columns, and then in those columns we're going to fill out all the possible combinations of true and false for each of them. So both owner and admin, just an owner but not an admin, not an owner but an admin, and then neither owner nor admin. We've got all the combinations here. And in that final column, over on the right, we put the return value of the method given those values for the inputs. And here we can see that this confusing conditional code is always going to be true, except when both the owner and the admin are false. Now, part of the value of a truth table like this is it allows you to easily kind of scan and see how the method behaves without having to interpret conditional code in your head. I don't know about some of you, you may have a really good Ruby interpreter in your mind. Mine, it depends on the day. Some days it's good, some days not so good. So a table like this is really helpful to understand code. There's also another advantage of truth tables, which is that we can figure out if two expressions are equal when their truth tables match. So remember how I told you that that initial condition is equivalent to the Boolean expression owner or admin. Now, you all just believe me, and I appreciate that, but now I'm going to prove it to you. Here we've got an extra column on the end with the truth values for that expression. And we can see that they match the same values as we have for the conditional implementation. Everything is true, except for the last row where it's false. That means we can now have confidence that our refactor to using a Boolean expression does not change behavior. This is a pure refactor. The implementation has changed, but the behavior has not. Now, if you're doing code review, GitHub allows you to embed tables in its markdown syntax. So you could leave a comment and put a table in there to show what you're trying to talk about. I love truth tables because they help me understand complex code that I struggle to otherwise understand, and because they also help improve my communication. They're a great way to talk about code with other people. So we've seen some confusing code, but let's look at some actual broken code. So we've got a feature where we want to forbid signed out users and untrusted IPs from accessing our website. And the code looks something like this. So we have a method, allow access to site, and we say not signed out and untrusted IP. I don't know about you, but that kind of messes with my brain a little bit. There's some double negative happening here. Signed out and untrusted IP are negative in English. And then we have them wrapped in parentheses with a negation sign in front of that. So one of our colleagues helpfully submits a PR where they decide to clean things up a little bit. instead of wrapping it in parentheses, let's just negate each of the individual conditions. It's still a double negative, but maybe this is slightly easier to understand. And you know what? That's a matter of opinion. What's not a matter of opinion, though, is that our colleague broke the build. This is not going to work anymore. The expected behavior, if we build a truth table, is that when both values are true, you are forbidden from accessing the website, but otherwise you have access. But if we compare the truth table for the new implementation, you'll notice it does not match at all. These two expressions are not equivalent. So a lesson from Boolean algebra tells us that De Morgan's laws, which teach us about how to negate compound conditions. So to negate a compound condition using De Morgan's laws, we first have to negate every clause. That's what our colleague did. Good first step. But you can't stop there. You also have to invert the operator that's in the middle. So if you're saying not A and B, then you would convert that into not A or not B. Notice that we have converted that and into an or. Similarly, if we have not A or B, that becomes not A and not B. So here's the original code before our colleague tried to change it. And if we apply De Morgan's rules, step 1, we negate each individual clause. That's what our colleague did. And then step 2, we invert the operator. It's now an or in the middle, not an and. And if we check this now in our truth table, we'll see that the truth tables now match. We now have a valid implementation that is equivalent to what we had before. So now we have our correct code, and we still have those two double negatives, but at least maybe it's slightly easier to read. Something that's nice about having the double negatives now at the individual clause level, rather than wrapping the whole thing, is that we could just alias those two, extract methods, and write them in the positive. And so now the code reads, who's allowed to access the website? If you're either signed in or you're a trusted IP, you get access to the website. So keeping in mind De Morgan's rules for compound conditions can help us write code that is much more readable. But it's also a tool that I use to help catch bugs. Anytime I'm writing code where I'm negating a compound condition, or if I'm reviewing code and I see that someone has negated a compound condition, I'm going to pay close attention. Maybe I'm going to scribble out a truth table. Maybe I'm going to look at the test suite. But those are areas that need maybe taking a second look, because it's very easy to make a mistake there. De Morgan's rules are not intuitive. They're not the thing that you would naturally do if you didn't happen to know about them. And so they're worth taking a closer look at code that would require applying them. And also, keep in mind that unless is a form of negation. So if you see code that says unless and then a compound Boolean expression, pay attention there, because that could also be a bug. So it's useful to look at code that has a potential De Morgan violation and maybe build out a truth table, maybe look at it manually. But you might be thinking, couldn't the test suite catch this? Shouldn't we have coverage? And then we don't have to do any of this nonsense. Well, yes, but are you confident that you have enough coverage to cover those? How do you know if you've written enough test cases to cover all the edges in a particular method? Combinatorics, which is a subfield of discrete math, gives us some tips. So let's say we have, again, a policy object. It has a can-read method here. And it says that you can read this article if the article has a public access policy or if the user is an admin. And we've written 4 tests to cover this. It allows an admin to access a public article. It allows an admin to access a private article. It allows a non-admin to access a public article. And it disallows non-admins from accessing private articles. So, sounds like we've covered most of the cases, right? Well, how do we feel more confident? Well, there are two inputs into this method. One, whether or not the user is an admin, and secondly, is the article public. Checking whether the user is an admin has two states. It's something that's either true or false. Simple enough. Whether or not a policy is public, though, has three states. It's true, false, or nil. That's because we have that safe navigation there. There's some uncertainty that's happening in this system. The field of combinatorics tells us that when we're building a compound state, we need to multiply the number of states in each of the underlying pieces. So in this case, 2 states times 3 states gives us 6 states. But we only have 4 tests. So I think there's a couple edge cases that we're not handling here. If I do something that's kind of like a truth table to list out all the combinations of inputs and outputs, you can see I've highlighted the 2 rows in the bottom. These are the 2 where we did not have a test case. And oh, look at that. Did not handle the nil case. I made that mistake. I'm sure none of you have ever forgotten to handle a nil. So dealing with combinations is not only something we need to do with Booleans. Consider something a little bit different. Here we have a constructor method that takes a couple of default parameters, a limit and a scope. Now, optional parameters add 2 states to your method signature, and we have 2 of those. So compound states multiply. 2 states times 2 states equals 4 states. There are 4 different ways of calling this method. We could call new just by itself. We could call new with a limit. We could call new with a scope. Or we could call new with both a limit and a scope. Did you remember to test all of those combinations? Probably not. So what can we do when we're in this situation where we've figured out that we have not enough test coverage? Well, I'm a big fan of Venn diagrams from set theory to illustrate this. The problem that we have is that we have a set of states and we have a set of tests. And ideally, we want those 2 sets to be equivalent. But our set of tests is smaller than our set of states. So visually, what could we do in order to make those 2 equal? There are 2 things that we can do. First, we can grow the set of tests to match the set of states. But secondly, we can also shrink the set of states to match the set of tests. It doesn't have to just be one way. So what does that mean for our problem? Well, our solution is either we can add more test coverage to handle, let's say, the nil case, or we can reduce our states. Just because you notice you don't have enough test coverage doesn't mean that you have to add more tests. Sometimes what this is actually telling you is that your code is trying to do too much. So in the case of our early example with the safe navigation, maybe what we really want is to check for nil earlier so that we don't have to deal with nil in this case, and that we're only dealing with 4 states, not 6. So now we know how many tests we need, but what about when we have to deal with really complicated tests? This is a technique that I don't use all the time. It's less frequent, but when I do, it's a real lifesaver. So here we've got a complex test. Don't feel like you need to read all of this code. It's not really relevant. But let me just describe the general structure of it. We have a series of nested describe blocks, and we've got some let declarations at a few different levels throughout. And then we also have a couple of tests that are trying to do some things. Anybody have code that looks like this in their code base? Yeah, we've got a few. If you're not the one who's written this, it can be really hard to exactly figure out, when looking at a single test, what data gets set up for that test. So here's a visual model that I like to use when I'm trying to understand what's happening. First, I'm going to list all of the lets in the file. In this case, we've got an organization, a user, an admin, a product, and an invoice. Then I'm going to draw lines to connect those boxes. Now those lines are not about active record associations. Instead, they're about which lets reference which other let. So in this case, the invoice let block references the user let block, and it also references the product let block. And we can connect them all, and we end up with this nice little diagram with boxes and arrows pointing to other boxes. What we've just built here is called a dependency graph. And I absolutely love these things. I use them in all sorts of different places. But here we're using them to analyze the let blocks in a test. So if we try to figure out what let blocks are actually going to get executed, first we have to look at anything that has a let bang in front of it. Let bang is eager, so that means that it will immediately get invoked no matter what happens. Unlike regular let, which is lazy and only gets called if you reference it. So shade let bang, that's immediately getting called, we know that. Now a lesson from graph theory tells us that when you evaluate a node in a dependency graph, you also have to evaluate all downstream nodes. So in this case, because organization is downstream from admin, we also need to shade that. This makes sense because the admin let block has a reference to the organization let block. It needs it in order to do the work that it has to do. So now we've set up our base state. Both of those values are going to get evaluated no matter what happens in your test. But let's look at some actual tests now. How do they add extra behavior on top of that? Well, the first test references the invoice let block. So we shade that. And remember, we have to follow the dependencies, follow all of those arrows. And so we go down, and invoice references user, which references organization, and invoice also references product. So we shade that. And would you look at that? That one little test actually ends up evaluating every single one of those lets in the file. Who knew? What about the other test? This one references product. So again, we have our base state with the admin and the organization, and then we shade product on here. We try to follow the arrows downstream, and there are none. Product does not depend on anything. So in this test, only the product, the admin, and the organization end up getting evaluated. The invoice and the user are lazy, they don't get invoked, and so that work does not happen. I'm a big fan of this kind of graph because, one, it helps me figure out what is happening in a test. It's not obvious sometimes that 20 or 30 let blocks might get called because only one of them is referenced in the test. But through a chain reaction, they all get evaluated. Secondly, it's important to note that you're not locked into the structure. This is reflecting how your let blocks are defined, but you can always define them differently. And maybe you notice, oh, the way that I have them structured causes this long cascade of dependencies getting evaluated. What if I structured things differently? If I inverted a dependency, or if I made one thing reference another, maybe you can change the structure, and now you have a lot fewer things that get evaluated. So if you're trying to maybe do some performance optimization, trying to limit the amount of calls to a database, this can be a useful exercise to try to simplify a complex test that is making a lot of database queries. One of the more powerful skills that I have as a developer is learning to break down complex tasks and working with them incrementally. And graph theory is one of the tools that I use to do that. This is my favorite. I've kept it for the end, and I'm really excited to share this one with you all. So if we have a large task, we might break it down into a series of sub-steps. Step 1, 2, 3, 4, 5. Simple enough, and then maybe work through them in that order. The thing with subtasks is that they're rarely a linear list. You can't always just work through them in order. In fact, most subtasks end up forming some kind of dependency graph. So here, step 1 might depend on step 2 and step 3 already being done before you can do step 1. Similarly, step 2 might depend on step 4, and step 3 might depend on both step 4 and step 5. So if we start with step 1, we just try to jump in and do step 1 as our task, Well, remember that evaluating a node requires evaluating all downstream nodes. And so what we end up is having to do every step in order just to ship step 1. And the whole goal of breaking a large task down into smaller subtasks is to be able to work incrementally. And here we started pseudo-incrementally and ended up just doing a single giant chunk of work. So let's look at an alternative way of doing this. Instead of starting from step 1, what if we start with step 5? We do step 5. Remember, we have to follow all dependencies, but step 5 has no dependencies. So it can be done in isolation. It will pass the eye. It can stand alone. You can ship this to production and maybe even just pause work, go fix a bug, and come back tomorrow and keep working on this. Similarly, we can do step 4. It has no dependencies. Ship that independently. That works. And now we can do step 3 because the 4 and 5 dependencies have already been done. So step 3 can be done in isolation and shipped on its own. Same for step 2. And then at the very end, we ship step 1 and we don't have to do everything else. Everything else has already been done incrementally, and our final step is step 1. A lesson that we can learn from graph theory here is that dependency graphs should be evaluated from the bottom up. You start with those terminal nodes that have no dependencies and kind of work your way back. When you work in that way, you can evaluate each node on its own without having to deal with any of the surrounding work that has to happen. And this is really powerful because it allows you to not only build steps independently, but you can merge them onto your main branch. You don't have to have a long-running branch with things that you have to reintegrate all the time. You can have them pass CI. You can ship to production. You can pause work, go do something else, and come back. And so it's really powerful for your workflow. For all of you who are wanting to take notes or look into these ideas later on, the fancy term for this sort of bottom-up evaluation is topological sort. You don't need to know this for this talk, but if you want to research it, this is the official name. Okay, let's look at a more complicated situation. We want to replace an image processing gem. And we've sort of figured out the steps are going to be 1, we need to change the gem in our gem file. 2, we're going to need to update the article model because the new gem has a different API. And then we're going to do the same thing for the user model. If we draw these as a graph, though, you'll notice something a little bit weird. These arrows form cycles. So if we change the image processing gem, we can't do that on its own. That's going to break because the article model needs to have is no longer using that API. But if we try to update the article model first, we don't have the new gem that gives us the new API, so we need to first change the image processing gem. So we're in a loop where each thing requires each other, and nothing can be shipped on its own. Graph theory tells us that cycles cannot be evaluated incrementally. So are we stuck? Are we just doomed to shipping this as one giant project? No. Remember, you're not locked into the structure. You can always modify your graph. And so in this case, why not introduce a 4th step to this work? We could introduce an adapter. So the first step would be we have an adapter object that wraps the old gem, but exposes the new API. This has no dependencies, so we can ship this on its own. We can merge it to master. We can go to production. Nothing breaks. Then, maybe a week later, we decide to update the article model. And it can use the new API because we have the adapter available. And so that can be shipped without having to do any other work. Merge that, ship it, we're good. Later on, we do the same thing for the user model. And then, because nothing is using the old gem API anymore, as a final step, we swap out the gem in the gem file, drop the adapter, and ship that as the final step. Each of these pieces was done incrementally. Each of these pieces was merged into main, shipped to production, maybe with weeks in between them, and we did not break anything. Now you might think, isn't this still a cycle? I see a big square on here. But remember, what matters are the arrows. If you follow the arrows, once you reach that bottom one, introduce adapter, there are no arrows out. This is, in fact, a terminal node. The fancy term for this kind of graph that has no loops is called a directed acyclic graph. Again, not super relevant unless you want to Google this later. And the pattern that we used, where we introduced an extra step that added a sort of wrapper or an adapter that allows us to work incrementally, often goes by the name the strangler fig pattern. This is a must-have in your tool belt if you're doing any kind of large-scale refactor or large upgrade project. You're going to want to use a tool like this. So there's a lot of other things that we could talk about from discrete math that informs the way that we work. We don't have time to go over them today, but I'm going to just quick shout out a few that I think are fun. One, if you're doing any sort of randomly generated ID and you want to know what are the chances that I'm going to have a collision here, and maybe naively you think, okay, I've built something and the chances are probably pretty low. Well, combinatorics has some tools to help you better understand whether or not that's actually the case. And there are some edge cases where that's surprisingly not true. If you want something to Google, look up the birthday paradox. Designing a database schema. What you often want when you design a database schema is you don't want invalid states. You don't want to have redundant data. And so some ideas from set theory and combinatorics can help us to better deal with that. Predicate logic is a field that's all about dealing with statements of truth that apply to all or any of a set of values. And so these can help us understand the all and any methods in enumerable. And speaking of all or any, we use those kinds of statements in communication all of the time. And so predicate logic and set theory can also help improve both understanding what people say, but also our own communication. If you've ever felt foolish because you've made a superlative statement, an absolute, and then somebody immediately corrected you by giving a single counterexample, predicate theory could have helped you with that. Predicate logic. So we've seen today a variety of ideas and tools from discrete math, Boolean operators, truth tables, De Morgan's laws, thinking about compound states and how they multiply, and a variety of ideas for working with graphs. The idea that evaluating a graph node requires you to evaluate everything downstream, that ideally you're evaluating a graph from the bottom up, and that it's totally fine to break the cycles in your dependency graph. Thank you for coming to this talk. My name is Joël Quenneville, and I am not good at math. I think we have time for a few questions. Yes, and the question is, where did I get the idea for applying discrete math to programming? I think that some of them I was already doing just in my day-to-day, and I didn't recognize it. And it took a conversation with a colleague about what is actually useful in discrete math, and realizing, wait a minute, you know, when I do reach into a complicated Boolean method, I will occasionally draw a truth table. That's something useful. Or recently, I've been really leaning into dependency graphs and how they can help me solve problems. I apply them to a lot of different situations. Here I showed two, dealing with lets in a test and working incrementally, but there's a lot of other situations where modeling a problem with dependency graphs is helpful. I'm a big fan of using a tool like Mermaid to draw out graphs. It's super easy, but if you're a little bit more old school, you might want to use something like GraphViz to just quickly draw these graphs. Or, you know, paper and pencil works well as too. Yes? So the comment was that if you use a shared example and then pass in expectations and result, that can make it read like a truth table. Something that I've been experimenting with is a custom RSpec matcher that allows you to pass in an actual like ASCII truth table as the value to the matcher. Still not sure exactly if that's going to be the developer experience bonus that I think it will be, but it might be more readable than 8 or 16 if blocks that are checking all the combinations of true and false. All right, question over there. Yes, the question is, if you use these terms from discrete math, does it come off as pretentious when communicating with colleagues? I will often try to avoid using the formal mathematical terms. Like I'm not going to say, therefore, we should convert our directed acyclic graph and build a topological sort. No one wants that. But I might draw a diagram and say, hey, if we work it in this order, you'll notice that we don't have to, we can do each piece independently. And maybe a link at the bottom to say, hey, if you're interested in how this works, check out this article on topological sort or something like that. So the goal when communication is you always have to keep your audience in mind. And if you're speaking to people who are probably not familiar with this, don't use the jargon. So that's a comment mentioning the test prof gem. And it sounds like maybe there's a tool there that can generate some of the dependency diagrams for maybe your factories or your let blocks. That sounds really cool. I'll have to look into that. I think there was a question over here.
Yes. Wow. All right. First things, this is an old reference. There's a Groovy framework called Spock. So if you're looking into that, it has that feature built in. I haven't looked at the implementation. I haven't used Spock in 10 years, but it does exist, at least in one test running. I think I've seen in others. And then my question is really, so what's the largest number of lets you've seen set up for a single test when you did one of these graphs?
Oh, the largest number of lets that I've seen in a test file. That's probably a scarily high number because I have seen test files that are multiple thousands of lines long, and they have lets defined at multiple different levels because at that size, you also have very deep nesting, and so you never know what's in scope or not. It can be terrifying.
Thanks.
Ooh, so were there any topics that I had to cut for this talk? And are there any good resources for this? Topics that I cut, I mentioned a few at the end. We had a little bit of combinatorics for dealing with collision detection, a little bit of set theory in combinatorics for designing a database schema. I think this is one that I would have really liked to talk on if I had had more time. And then some of the predicate logic stuff, I think, is also really helpful. I love it when some models that we have from mathematics or software are useful not just to write code, but also to improve our communication. Because at the end of the day, as developers, we're communicating with computers and we're communicating with people, and we need to be good at both of those. As far as resources, I think brilliant.org has a course on discrete math. They have kind of a wiki section that I think is pretty accessible. That's publicly available. And I don't know if the course itself is paid or not. All right, I think those are all the questions we have time for today. Thank you for coming to the talk. Feel free to come and see me afterwards. Yeah, thank you.